Next photo shows Mount Fuji of the United States. Photo taken 40 years ago. Mount Fuji in Japan is well known as an extremely beautiful mountain, very symmetric, pyramid-shaped mountain. The closest thing we had in the United States to that mountain in terms of symmetry and beauty was this one. His name was Mount St. Helens. On March 20th of 1980, just a few days from exactly 36 years ago, a small earthquake, 4.2 on the Richter scale, probably not picked up or detected by any human being other than those watching seismometers. Very subtle. Many earthquakes are occurring in that particular area, but this one was located 15 miles away from Mount St. Helens and about 5 miles beneath the surface. Volcanologists, those who study mountains that explode, volcanoes, became immediately interested. The possibility existed that, in fact, Mount St. Helens was about to come back to life again. We knew that about every 200 years, Mount St. Helens had erupted in the past. It had a long history of that. And it had last erupted 180 years before. So it's about that time that Mount St. Helens might erupt. The last time that an eruption had occurred in the contiguous 48 states was 1914. And since that point, 1914, we'd invented seismometers which could study such things more carefully. Scientists were very excited. This is a possibility. Next. The mountain was well known as a volcano. You can see a lava flow here on the right. The fact that it was a volcano was well known. The next day, March 21st, several earthquakes were detected, each one getting slightly closer to the mountain and at a slightly lesser depth. The day after, several more. March 27th, within 1 week of the first earthquake, the mountain was now under harmonic tremors, meaning there's over 1,000 earthquakes per hour that were occurring, the kinds of earthquakes that indicated that there's churning lava underneath the mountain. The earthquakes had moved to directly underneath the mountain and were moving directly up into beneath the mountain, only about 1.5 miles beneath the surface on that date. Next. March 30th, 3 days later, 3 days after harmonic tremors began, there was a small eruption that created a crater down there on the seen on the lower left, tossed up some ash into the atmosphere. This sealed it. We know for sure this mountain is about to erupt. So scientists converged on this location from all over the world, especially in the United States. More volcanologists converged on this point than had ever centered on a volcano before. Next. USGS set up facilities in Vancouver, Washington. They set up the temporary facilities here to monitor the mountain. Most people probably wouldn't even have noticed the thing there. I couldn't help but take the photograph on the bottom there on one of the outside one of the rooms was volcano control. How hubris! What the hubris of humans! But they set up, among other things, on the left. There's on the far left, we see a machine that's actually monitoring 3 seismometers at the same time. Seismometers at a distance, radioing the information to this site so that we could watch. Actually, 45 seismometers were set up around the mountain so we could pinpoint the exact location of a particular earthquake to within a few feet of its actual location, both horizontally and vertically in the ground. Then, just to the right of that, we had set up tiltimeters all over the place. This would be lasers that shoot a beam several miles to another location where there's a mirror. The mirror bounces the beam back to the detector next to the laser, so that if any motion occurs between these two positions, the laser can measure that. In fact, it's sensitive enough that if you had a mile-long ruler and slipped a dime underneath one end, the tiltimeter would pick it up immediately. So in this way, we were able to measure tiny motions of the mountain itself to determine if in fact the mountain was deforming as a result of lava moving up into the mountain. At the same time, the USGS, the United States Geological Survey, began the process of evacuating residents from around the mountain. They set up a red zone of a couple of miles around the immediate, the crown of the mountain that was where no one was allowed, scientists or anyone else, because of the high danger. And then beyond that, going out 13 miles away from the mountain, the equivalent of the distance between here and Clarksville, is a blue zone. Everyone was vacated, or at least attempts were made to vacate everyone from these particular areas, and the only people who were allowed into the blue zone would be those who promised that they would always keep the mountain in sight. In other words, if an eruption occurred, they would see it, and they had to be able to get out of the blue zone within 20 minutes. You're going to see how important that particular rule is. Next. Eruption on the 30th of March left the small crater that you see up there on the upper left. Over the next few weeks, that crater increased in size, indicating that the mountain was deforming and the top was actually collapsing into the mountain. So the larger of the two craters here is that little one, now expanded. And then a second crater showed up. And then the two craters fused together, and you can see a plane down there for scale. Very large deformation in the top of the volcano. It was, volcanologists knew long before this that the mountain was going to erupt, but we know something's about to happen here. Next. May 18th, 1980 was a Sunday morning. That particular morning in Southern Baptist churches across mostly the South, the bulletin photograph was actually the photograph of Mount St. Helens. On that particular morning at 8:32 a.m., 17 seconds after the minute, an earthquake occurred on the mountain. Next. The photograph on the upper left is taken from a plane who's circling the mountain at that moment. The earthquake occurred. The mountain had been deforming to the north. We knew from the seismometers that the north part of the mountain was bulging outward. A few days before the eruption and up to the eruption, 50 feet per day, it was actually moving outwards, looking from the side like a pregnant lady. Mount St. Helens was a pregnant lady there. The earthquake occurred right at the base of the belly, breaking the supporting rocks to this big bulge. And so at the moment the earthquake occurred, you can see some rocks falling off of the summit of the volcano into the crater. A moment later, as fast as it took a person to take photographs in the plane, that all the stuff to the right had fluidized and started moving down the mountain. One half cubic mile of rock slid down the side of the mountain. At its peak, it's moving at 200 miles an hour down the side of the mountain. Two photographs taken from 11 miles away from the side show there's two collapses. The first avalanche, and then there's one immediately behind it. You can see them as bumps. One of the lower avalanche is the lower bump with the red arrow pointing to that. The second avalanche is the bump with the arrow to the left. And then just a moment later, you see that the upper one has moved down the mountain, and the lower one has moved less far because, in fact, it's gotten to the bottom and is slowing down. It's now slowing down to about 150 miles an hour as it slides down the side of the mountain. Next, it's a half a cubic mile of rock that filled the valley in between the mountain and the next mountain, up to 700 feet of rock put in there in just about 12 seconds. You're looking in the lower picture at Mount St. Helens in the background. The material came straight towards you, and looking at the photograph, it pushed all the water out of Spirit Lake and then filled Spirit Lake. Spirit Lake came back down into that location again, now 250 feet higher than it was just 2 minutes before. Next. Now, the real event then started after that. What we did is we just took a half a cubic mile of rock and took it off the top of the mountain very suddenly. And what had been happening before this is that kind of like thinking about a can of soda that you heat up to 500 degrees centigrade and shake about 1,000 times per minute for several weeks. Now, just take the top off of it. That's basically what happened here, okay? We have slid a half cubic mile of rock off the top of the material underneath. Material underneath was already at temperature of about 500 degrees centigrade. It was kept as water. Any water in it was still water because of the pressure. But as soon as the pressure was taken off, it flashed into steam and created an explosion. Here you see the beginning of that explosion. It's the equivalent of a 20 megaton bomb, 20,000 atom bombs going off at a moment. Okay, next. You see a picture from 13 miles away, and we're going to now see a series of 4 of these photographs as quick as a photographer can take them. Now, in point of fact, what's kind of interesting is the photographer is escaping for his life. He's in a vehicle traveling as fast as he can travel, and he does survive out of this. But he's taking it out of the window of his vehicle as he's going along, as quick as he can snap the pictures. So these will show the eruption. You can see the slide that's going down the mountain, but then behind it is the eruption. So next 4 photos, 1, 2, 3, 4, shows the explosion. It's going to propel vaporized water at 300 miles an hour across the landscape. Because the collapse had occurred to the north, it's not going to direct the eruption straight up. The explosion went laterally to the north. This was a surprise. This was not what people expected. And it's going to cover the 13 miles of the blue zone in 8 minutes. So your 20 minutes to get out, forget it. You're done. You're finished. You can't get out of there if you're in the path. And even though this person was lateral to that, the eruption went off to the side as well. It would overcome the next photo I don't show it here. The next photo shows the thing going over the top of the car. And then he struggles in the dark to try to escape down a mountain road as fast as he could. The next photo shows another perspective from another photographer at a different perspective. You can see at the red arrow these white trails. These are rocks being tossed out of the mountain. They're house-sized boulders being tossed 13 miles away from the mountain. Next photo. I'm standing on one of those boulders in Coldwater Lake, looking at another boulder in Coldwater Lake that had been tossed out in this eruption. 13 miles. If that eruption was here at this location, it's tossing the boulders, house-sized boulders, into Clarksville. Almost twice as far as Claremont is away from here. It's an astonishing power. Next. This is going to be a series of photographs from a satellite. The shock wave, this is a boom, boom, okay, an explosion. But it's too big of an explosion, too powerful of a sound wave to be heard by the human ears. The human ears are just too small for this enormous sound wave. The sound would have to travel for 75 miles before it would reduce in power enough that a human ear could hear it as a sonic boom. And it would be heard for up to 150 miles away from the mountain as a sonic boom. But these are photographs from a satellite. The shock wave is going up from the mountain, hitting the troposphere-stratosphere boundary, pushing the clouds out, basically pushing what was at the temperature to produce clouds up further, and the clouds disappear. It sort of dissipates the clouds and generates a whole nother set of clouds in its place. So we're going to see 3 photographs over about an hour's period of time as the effect of this this boom. Next, next, and next. So it's over the state of Washington. It is moving at the speed of sound, 500 some feet per second. So over the next hour or so, it's going to deform the atmosphere of the Earth. Next. The other effect of this is that this steam explosion is going laterally across the landscape at 300 miles an hour. That's bigger than it's bigger than hurricanes, and it's bigger than most tornadoes. An F4 to an F5 tornado would have a wind velocity similar to this. But this is a single wind velocity of 300 miles an hour moving across the landscape we deduce from what it did to plastics and that sort of thing, 500 degrees centigrade. So what it's doing when it hits a tree is it vaporizes the leaves, the branches, the bark, and leaves only a toothpick that remains, breaking the thing off at 300 miles an hour and laying the trees down in the direction of motion of the blast, and leveling 156 square miles of forest in 8 minutes. It's the equivalent, we estimate, of over 4 billion board feet, enough to build 300,000 two-bedroom homes. It took that out in 8 minutes. Next. This is a picture of some of those logs, and for scale, that little oval down there in the lower right circles a couple of people, a couple men. See the size of these. Some of these trees are 8 feet in diameter. It just didn't matter to this stuff. It just laid them all out flat. Next. Here is a satellite photo showing the vegetation around the mountain before the eruption and after the eruption. You can see before the eruption, the vegetation is showing up in a false red. So you can see that's forest. Down below, you see the 156 square miles of forest taken out in 8 minutes. So you can see where it went, straight to the north and laterally. Next. Then the main eruption begins. That was just the prelude. Now, once the pressure was off, now the eruption could begin. Now, for the next 9 hours, the volcano will release the equivalent of 1 atomic bomb of energy per second for 9 straight hours, pulverizing a total of 1 cubic kilometer of rock into ash, fine microscopic particles, and tossing it 60,000 feet up into the atmosphere. Next. This is a satellite photo showing the volcanic ash. We're going to see a series of 5 photos that will show how the ash went up into the atmosphere, was blown by the westerlies across the state of Washington into Idaho and into Montana. Next, for five in a row here. You see how it's blown across the states to pretty much its final location. Next, in the city of Yakima, Washington, 80 miles to the east at noon, just a few hours after the eruption, the ash was so heavy that the streetlights came on, and we've got ash coming down. It's dark. It's in the middle of the night in Yakima, Washington. Next. A tragedy, of course, there's 57 people that lost their lives. One was a resident in the lower right. Harry Truman lived on Spirit Lake. He refused. He was the only resident who refused to leave. We'll come back to him later, but he said he wasn't going to leave his lodge. So he is buried under several hundred feet of dirt and then a lake, and he was dead within a few seconds of the eruption. Also on the upper left was one geologist who was on station opposite the volcano, observing the volcano, David Johnston. In fact, we know the exact moment of the eruption because he picked up a radio and said, "Vancouver, Vancouver, this is it." And that was the last we heard of him. He was blown off the top of that mountain and killed within, again, a few seconds of the eruption. The rest of them, 55 others, were people that came into the Blue Zone to take photographs, either because of curiosity or because they were news people. One of the examples is this camper that's shown here. It is faced directly towards the mountain. A man and a woman are in the camper. The man is at the steering column with a camera sitting on the steering column, and they were boiled alive in probably about 90 seconds after the eruption began. They are some 5 miles away from the mountain. Next. Now, I didn't really come here to talk about Mount St. Helens, but Mount St. Helens gives you a little bit of an idea what the power of a small volcano is, what a mini volcano is. And so with that kind of information, you got some idea what a volcano is, I want to talk about volcano history. And backing up in a broad sense, there's different worldviews on history. There's the idea that all of Earth history is uniform, that what's happening today is the way it's always been in the past, that there's no, things change all the time, but on the average it stays very uniform. This is a uniform view of history that is the predominant secular view of Earth history. It's the naturalistic view of Earth history. Secondly, we have a cyclical concept of history. Common among the Eastern religions is the idea that, things do change, but they change and come back to the beginning, and there's this overall, in the biggest sense, there's no real change, but there's a cyclicity to things. The size of the cycle varies, but things change but come back again. So overall, on a bigger scale, it's sort of like a uniform perspective. And then finally is what is called a linear view of Earth history, which is that Earth history began at one point, goes to another point, and is not staying constant. In fact, there is a consistent change in history. This is unique to a biblical view of Earth history, where it has a beginning, it has an end, and there is a pattern or a trend to it. So with these kind of philosophical thoughts or interpretations, modes of interpretation in mind, let's look at the history of volcanoes to see which of these it actually fits. Next. Mount St. Helens in 1980 pulverized 1 cubic kilometer of rock to produce ash. So my first look at volcanoes is to examine the issue of ash production. Got to be careful how you say that. How much ash does a volcano produce? We're going to look at the ash of a volcano. Mount St. Helens produces a cubic kilometer of ash. 11 years later, we have a very substantial eruption, Pinatubo in Indonesia, which pulverizes 11 cubic kilometers, 11 times the amount of ash produced by Mount St. Helens. A famous eruption back in 1883, Krakatau, destroyed an entire island, actually produced several islands out of one. It's generated, we estimate, about 21 cubic kilometers of ash, 21 times what Mount St. Helens pulverized and sent into the atmosphere. Tambora, considered the most powerful earthquake of recent times, let's say post-Christ times, the Common Era, in 1815, pulverized 160 cubic kilometers of rock into ash. If you look at Vesuvius, that's a famous volcano, took out Pompeii, a similar sort of steam explosion going down over Pompeii took out Pompeii. A mud flow off another side of the mountain took out another city, Herculaneum. Very famous in history, but it's estimated that it generated about 10 cubic kilometers of ash, about 10 times the size of Mount St. Helens. Santorini, another very famous eruption, also known as Thera, also known as the Minoan eruption. About the time the people of Israel were coming out of Egypt, this eruption destroyed, we were pretty sure, the Minoan civilization, just wiped it out. It's an incredible eruption. It is thought to be about 100 times the size of Mount St. Helens in terms of ash production. Then another one that might be somewhat familiar to you, the beautiful Crater Lake out in Oregon, is to create that crater, is actually the generation of about 100 cubic kilometers of ash. That's going back a few thousand years before Christ. So really, for the last 4,000 years, it doesn't look like there's any sort of a trend. It might be a little bit of a trend of increasing size with distance away from us, but not a lot. Next. Now, all of these volcanoes that I just showed you on the previous slide are sitting in very particular places around the world. Krakatau, Tambora, and Pinatubo are actually in the Indonesian island area. Mount St. Helens and Crater Lake are both cascade volcanoes in the western United States, and Vesuvius and Santorini are just south of Europe. In every one of these cases, they share something in common. Next. What they share is a piece of ocean crust is stuck underneath the continent at that point, and the ocean crust is melting, and the material is rising to the surface to generate these volcanoes. So, for example, Mount St. Helens is one of the Cascade volcanoes. You've got a number of them up there. Mount Adams, Mount Hood, Mount Jefferson, Mount Shasta, Mount Rainier. All of these are Cascade volcanoes from a piece of the ocean crust of the Pacific Ocean crust that's stuck underneath the North American continent, melting and producing those volcanoes. Similarly, in the Indonesian islands, that's what the Indonesian islands are, is a bunch of islands that are volcanoes produced by Indian Ocean crust on one side and Pacific Ocean crust on the other side, underneath the continent or the ocean there, and volcanoes are coming up as a result. Likewise, underneath Europe, to the south of Europe, there's a piece of ocean crust that was north of Africa that's now stuck underneath Europe, producing those volcanoes. So these volcanoes all share that kind of story or origin. Next. If we go back further from Mount St. Helens, the red there, you saw where the ash landed in Mount St. Helens. Crater Lake, with 100 cubic kilometers, covered the area seen in yellow. If you go back further from Crater Lake, back to before 2000 BC, you've got the Bishop Tuff that covers the area in green, an eruption of quite large magnitude, creating 600 cubic kilometers of rock pulverized into ash. Before that, older than that, are two eruptions at Yellowstone National Park. The smaller one is the Lava Creek, produced the Lava Creek Tuff, 1,000 cubic kilometers of rock pulverized into ash and sent up into the atmosphere. That is a block of rock 6 miles high, 6 miles on a side, a cube of that size, pulverized into ash, covering a significant part of the western United States. As a matter of fact, if that eruption were to occur today, it is estimated that it would have a 100% kill everything west of the Mississippi River. Every animal and plant would be dead west of the Mississippi River from that one single eruption. There's an older eruption that's 2.5 thousand cubic kilometers, which is also coming out of Yellowstone. Next, if we step back further, we have the Painted Desert in southeastern United States that has an estimate. Some of it's eroded away, so we don't actually know the full extent of it, but something in excess of 10,000 cubic kilometers of rock pulverized into ash and dumped over the western United States to produce the Painted Desert and related formations. So when you look at the last 4,000 years, it looks like a linear Earth history. But if you look at the stuff before that, we've got really big eruptions that are occurring before that, which is suggesting a non-linear, a non-uniform or linear history. Actually, it looks exponential. Things are getting really big in the past as you go back. Next. There's another way to measure the size of eruptions, and that is with the lava that pours out. Forgetting the pulverized rock in the form of ash, we also have liquid rock that moves out of some volcanoes. Now, actually, the main eruption of Mount St. Helens on May 18th didn't produce any lava at all. But over the next 15 years, it gradually began building a new cone, a new volcano in the collapsed cone of the old volcano. And it actually added over time about 20 cubic kilometers of lava. So we're sort of cheating by giving it a lot of time to do this. But over time, Mount St. Helens produced 20 cubic kilometers of lava. Another eruption in the Navaruptu in Alaska in 1912 produced an estimated 30 cubic kilometers of material. If we look at some Iceland eruptions, they're about 20 cubic kilometers of lava. These are actually called flood basalts, situations where an eruption produces a lot of lava very quickly. The Crater Lake is another example, produced 100 cubic kilometers of ash, but only about 46 to 58 cubic kilometers of lava. Next, again, over the last 4,000 years, it doesn't look like a whole lot of difference. Iceland is sitting in this position. It's not like the other volcanoes, so it's actually a different type of volcano that can generate these flood basalts. If you go back further than 4,000 years, next, we again get a different picture. There's a little red dot over there on top of the little yellow box that represents the amount of lava generated by Mount St. Helens, 20 cubic kilometers of lava. The Columbia River basalts that are older than Crater Lake, a bit older than 4,000 years, produced 175,000 cubic kilometers of lava. There's about 156,000 square kilometers of area in Georgia, okay? This would mean you would put a sixth of a mile of lava over all the state of Georgia. That's how much lava is generated by that eruption, the Columbia River basalts. Again, the one that's missing underneath there, I don't remember off the top of my head. But it's a green one there. It's much bigger than the yellow one. Then an older one, an even older one, is the Karoo flood basalts. 100 million cubic kilometers of rock generated from one eruption. This is an astonishing volume of rock. Then if you look at the amount of rock generated to produce the current ocean crust, we have about 2.5 billion cubic kilometers of lava. This is 100 million times bigger than Mount St. Helens. 100 million times bigger than Mount St. Helens eruption. So it appears that although the last 4,000 years has been maybe uniform, if you go back a little bit before that, it is definitely not. We got some really big things happening on the Earth. Next. A third way to measure the power of an eruption is by how much crust it breaks, how much of the surface of the Earth it actually shatters in the eruption. Mount St. Helens didn't do anything at all. All that happened with Mount St. Helens is molten rock found old passageways, old pipes that it had used 200 years ago, 400 years ago, and it found those old pipes and melted its way through the plugs in those pipes and then erupted. And that's the case with all of those volcanoes that I was just referring to. They didn't do any additional breaking of crust. They were able to take old conduits and follow the conduits and erupt the lava onto the surface or create the eruption in that fashion. However, there are examples, which are older, that in fact the crust was ruptured. Here's the idea. You've got lava coming up from below, and it really wants to get up to the surface, but there's rock in the way. So it's got several choices. It can go through cracks that are already there, which is what Mount St. Helens did, or it can shatter the rock, can break its way through the rock, or if it can't quite do that, but it can lift the rock, it can lift the rock above it and then go laterally, creating a sill. So in Death Valley, for example, what's shown there is a sill that's about 800 feet thick, where it picked up all the rock above it and then shot the lava, if you wish, in between rocks that already existed. That takes a certain amount of energy. Even more energy is required to crack the rocks and break through to the surface. Next. So the volcanoes I've already referred to in the last 4,000 years, none of them broke the crust. But if you look at older eruptions, we find many examples of cracks of the crust. The next oldest one, again, sorry for the computer thing, the Columbia River material is the next oldest than the more recent eruptions. And that 500 refers to the length of the cracks that it produced in the crust. It actually cracked the crust for 500 kilometers, creating fissures that were 300 miles long away from the center of the eruption. Now that's a lot of power. Then the next oldest one is the Deccan in India that produced 700 kilometer long cracks in the Earth's crust. The others are older than that, most of them in the range of about 1,000 kilometers, cracking the crust in all directions for 600 miles around the eruption. And the biggest one that we know of so far, I mean, we've just begun to discover these things, is called CAMP, the Central Atlantic Magmatic Province. It occurred when North America, South America, and Africa were together, and it shattered the crust for 3,000 kilometers away from the center in all directions. That is the distance from Atlanta to San Diego. You cracked, have an eruption here that cracked the Earth's crust all the way to San Diego in one direction, all the way to England in the other direction, all the way to Venezuela in the other direction, all the way up to the north of Greenland in the other direction. That's the power of that eruption. Next. In fact, in the state of Georgia, if you look at the geologic map of Georgia, those red marks there are the radiating dikes, the cracks in the Earth's surface from that eruption, which was about 2,000 kilometers away from our current location, creating cracks in the rock and inserting into the rock the lava from the eruption. Next. So, measured in three different ways, we have whether it's pulverized rock sent up into the atmosphere as volcanic ash, or whether it's flowing of lava over the surface or cracking of the Earth's surface. We've got a consistent story that volcanoes for the last 4,000 years have been about the same size, uniform Earth history. But something occurred before that, and the more you get back older than that, the bigger the volcanoes become, and by orders of magnitude, by thousands to millions of times the size. Next. There is another way to measure, another independent way of measuring the power, and that's by means of diamonds. Diamonds are found in certain rocks called kimberlites. Kimberlites are rocks formed at a great depth beneath the surface. We know that because we know what it takes to make diamonds. We know that because we can create diamonds in the laboratory, so we know exactly the conditions necessary to make a diamond. You need the pressure that's equivalent to 10 kilometers or 6 miles of rock stacked on top of something. So you've got to be buried 6 miles beneath the surface. Got to have pure carbon. But there's one other thing that you need, which is really cool. If you do this in the laboratory, if you create diamonds in the laboratory, you can produce the pressure fairly easily and produce the diamond, but there's one more piece to the puzzle. You've got to quench it just right, which means you've got to cool it. You got to take the pressure off and the temperature off at just the right rate. If you do it too fast, the thing shatters, like putting hot glass into water. Your diamonds will completely shatter if they're cooled too quickly. If you do it too slowly, it just reverts to graphite and never becomes a diamond. And in the laboratory, we know that you have to do this in 5 to 10 hours. You got to quench it. Means you got to take it from the equivalent pressure of 10 kilometers beneath the Earth's surface to the Earth's surface pressure, and from that temperature to the temperature at the surface. And you got to do that in 5 to 10 hours. If it takes you longer than 10 hours, you got graphite, no diamonds. If you do that too quickly, you get shattered mess. You don't get anything that's usable. It turns out that diamonds that we find are associated with kimberlites. The kimberlites come out of these vertical holes, these pipes that go all that distance, 10 kilometers down, and these kimberlites were shot out of these holes in order to be quenched, in order to get from 6 miles down to the surface within 5 to 10 hours at its maximum speed, which would have been about the time it got to the surface. It's moving at 60 miles an hour. It's actually shooting upwards at 60 miles an hour into the crust of the Earth. There's a place in Canada where there's a 35-foot diameter hole of this nature where the material came right out of the ground and in the atmosphere exploded because of the sudden decrease in pressure and rained diamonds down over a 20-mile diameter area around that hole. Diamonds can only be formed in this fashion. They've got to be moved upward at extremely high speeds. 60 miles an hour is pretty high for moving rocks. Next. So, what we've got here is we've got something with enough power to pulverize thousands of cubic kilometers of rock and drop ash over continents in size. There's something the size of continents. We've got something that's powerful enough to exude millions of times as much lava as Mount St. Helens did in the matter of a few days. It's got to be something with enough impulse, enough power to crack the Earth's surface for thousands of kilometers. It's got to be something that raises kimberlites at tens of miles per hour from great depths to the surface. It's got to be something that actually generates about 200 cubic kilometers of lava per second to generate the ocean plates. There is one thing we know of that can do that. There's one theory out there that actually gives us sufficient power, is moving things fast enough to make this happen, and that's catastrophic plate tectonics that was alluded to a little bit before. A model that actually has the Earth's interior moving, rotating fast enough to bring material up to the surface to produce our kimberlites, bringing it up with enough force to crack the Earth's surface over thousands of kilometers, and to produce enough lava on the surface to create the flood basalts. But there's a side effect to this phenomenon. It does all these things, but it also, by our estimation, would raise sea level about 1 mile, flooding the Earth's surface with a global flood. So the only way we know of to explain the story here of these earthquakes, of these volcanoes, is the global flood spoken of in Genesis chapter 6 through 9. Next. The Bible speaks of that uniform theory of history in 2 Peter. It says, "There shall come in the latter days scoffers." People making fun of y'all. Scoffers saying, "Where's the promise of his coming? For all things continue as they were from the beginning of the creation." That's uniform theory of Earth's history. That's Harry Truman. Harry Truman was sitting there in that lake in sight of Mount St. Helens. He said, "I'm not going to move." He's an octogenarian. He's been there for a number of decades. He says, "That mountain has never exploded in my lifetime. It's never exploded in my parents' lifetime. It's not going to explode now. All things continue as they were from the beginning of the creation." That's the uniform theory of Earth history. That's the theory that most people, not just Harry Truman, but that's what most scientists follow. But the Bible says this: they are willingly ignorant. Not just ignorant. They know the truth, and they're ignoring the truth. This, they're willingly ignorant, that by the word of God the heavens were of old, they're ignoring creation, and the world that then was, being overflowed with water, perished. People that know about volcanoes, geologists that know about volcanoes, know something, that is that there's a non-uniform Earth history with regards to volcanoes. There's a time in Earth history when the volcanoes are much bigger, much huger, ridiculously huge, to be explained by any theory of uniform Earth history. But they are willingly ignorant of the fact that this is a time in Earth history when there was a global flood. The passage goes on to say, the Lord is long-suffering, thankfully, to usward, not willing that any should perish, but that all should come to repentance. So he's holding off because there's another judgment to come. He promised he would never again destroy the earth by a flood, but he didn't promise that there wouldn't be another way of destroying the earth, and it's going to be by fire. Something a little more similar to volcanoes. Something with even more power than that to destroy the earth and, in fact, the entire heavens. But the day of the Lord will come as a thief in the night, in which the heavens shall pass away in a great noise, and the elements shall melt with a fervent heat. The earth also, the entire earth, and the works therein shall be burned up. Harry Truman didn't believe the warnings because he believed in a uniform theory of Earth history. That is not the truth. The truth is a non-uniform theory of Earth history. The earth is what the Bible says. It was created in one way, it's been deteriorating, and it's heading for a destruction next. God judged by a flood in the past, and we've got definitive evidence of that in the volcanic history of this planet. God didn't lie about that judgment. He told us in His Word of that judgment and why He brought it to pass. So we know He has the power to judge. The God who lives and cannot die is the God who has still got the power to judge. In that same Bible that has told us the truth about the past, He's promised that there's a judgment to come by fire. He's already waited. He's been long-suffering. He's waited 4,500 years since the first judgment. He's waiting for one moment. There's going to be a moment when He stops waiting. He's made a way for us in the meantime. He's made a way out. The people have been warned. We've been warned. There is a way to escape that judgment, and it is through the man, God, Christ Jesus. Accepting Him, what He did for you. And you can't save yourself any more than Harry Truman can save himself from that mountain that collapsed upon him. You cannot save yourself from the judgment that is to come, that could be just moments away. But God can, and God's made a way. Jesus Christ was sent to this earth to take your punishment that you deserve in that judgment and beyond. And He has made a way that all you have to do is accept what He has done for you. Have trust that what He did for you is sufficient to get you through that judgment, and He will save you through that judgment. He's made a way for you. Are you ready? Are you ready for that judgment? Let's pray.